Hello, hello. Mic testing. 1 2 3 1 2 3. Okay, I'm live now. Can anyone confirm if audio, video, etc. looks fine? And I was able to solve like 5 problems. C was a bit tricky one. And I'm planning to discuss the problems that I solved A, B, D, E, F. C, I can briefly share what I have seen other people doing, but yeah, that's where we are. So, can anyone confirm if audio, etc. looks fine before we get started? Hello. Hello. Like also people in the chat, like how many problems were you guys able to solve? That will give me fair set of idea which problems to focus a lot more on and which problems we can quickly pass. And yeah, like contest was kind of like gas forces as well. D was also like do something, get an easy. I like D. Sorry, I like F. E was also some form of construction and just think it will get an easy. So overall, not a big fan of the complete problem set, but that's okay. I haven't read GNH, so cannot comment about it. So, like F was a bit interesting kind of data structure type of problem. While all of the problems were mostly like guess something if it works, and if it works, submit an AC, and that's okay. Yes, this would be recorded, and the video would be available on my YouTube channel, so you can find it later on here. And yeah, so like people in the chat, like how many problems were you guys able to solve? We will spend a couple of more minutes and then we will start discussing the problems. Hello, and also can anyone confirm if audio, video, etc. looks fine? Okay, I solved 5 problems: A, B, D, E, F. So those will be the primary problems that I'm planning to discuss for. And to be frank, the answer for all of this problem from me is like, okay, this got an AC and that's it. So this is where we are. And yeah, so a couple of more minutes and then we will get started. Feel free to ask anyone if anyone has any questions. Yeah, like is this contest hard? To me, it looked more like an ad hoc problems. So relative and ad hoc at times tends to be a bit hard. That's what I would say. And yeah, I think okay, let's get started. Yeah, I could not also solve C on this is okay. So problem A, the equalizer. To settle a long time feud, Sonak and Yes decided to play a game on an array A of n integers, with Sonak going first. The player takes turns and the last player to make a move wins. On a player's turn, he chooses some AI greater than 0 and decrements it by 1. To make things interesting, Sonak is allowed to use a special move at most once during the game. This move replaces his normal turn. When used, all the elements AI are set to a special value k that is initially given. So this is where we are. So it says we are given an array A1, A2, A3, A4, A5, and so on. In one move, a player can choose any index and subtract it by -1 as long as the original value was greater than equal to 0. And this is where we are. And we also have, like, player 1 also has a special move where they can make all the elements equal to k. And it asks like will win the game. So the idea is as follows. Like either we make all the elements equal to k in our very first move, or we will never use the special move and always subtract -1. First, let's see who wins if we never make all the elements equal to k. Then if, for example, we have 2, 3, 5, 6, then some of these elements would be the number of total turns we will have, right? So if we look at 2 plus 3 plus 5 plus 6, it's around 16, which is total number of turns. And every time, like whenever someone decreases -1, the sum decreases by -1. 16 becomes 15, 15 becomes 14, and so on. And because both the players are taking an alternative turn, player B would win always because the sum is 16. So the idea is, first let's look at sum of all the elements of A. If this is odd, then if we never use the special move, then also we will win. Because if there are 5 turns, player A will make sum from 5 to 4. Next player will make sum of all the elements 3, and so on. Like basically total number of what is the sum of the elements is what is the number of turns you can play, right? For example, you have 1, 1, 2, 3. Doesn't really matter in which order you play. You can make 3 equal to 2 in the first turn. Then the next player can make 0 equal to 1. Then you can make 2 equal to 1. And then the next player can make this 1 equal to 0. You can make this 0. This 2 becomes 0. And this 1 becomes 0. Like the number of turns is fixed. Doesn't really matter which element you choose. So if sum of all the elements is odd, then this is the total number of turns you can have. So like if you are starting, you will win. So, and if sum of elements is even, if we don't use the special move at all, then we are going to lose. And what I'm saying is, if you have to use the special move, then do it in the first turn as well, only. So if you use the special move in the first turn, when player B starts, like the total number of turns would be k into n after you use the special move. And because you have also used your turn, like this would be the total number of turns. Now, if this is odd, we win, player 1 wins. If this is even, the player 2 wins. So overall, this would be the idea for this problem. Let's look at some of the elements. If sum is odd, then we win. Otherwise, if we use the total operation, then n into k would be the number of turns that we'll have after we use the operation, and one turn would be done to apply this operation. Otherwise, if number of turn is also odd, then also we win. Otherwise, we lose. And this was problem A. Any questions, anyone on problem A before we jump on to the next problem? Okay, then in that case, let's move on to problem B. It says flip the bit easy version. This is the easy version of the problem. The difference between the versions is that in this version there is exactly one special index k equal to 1. You can have only if you have solved all the versions of this problem. Like hacking doesn't really make sense because it says hacks are disabled on A to B. You are given a binary array A of length n and k special indexes p1 up to pk. It is given that values ai of all the element at special indexes are same. In one operation, you can choose a range L to R such that the range contains at least one special element index and flip all the bits ai aj for L less than equal to j less than equal to R. Flipping a bit changes 0 to 1 and 1 to 0. Let x denote the value at special indexes before any operation is applied. Find the minimum number of operations required to make all the elements equal to x. So this is like basically we have given an array. In this case, we have one special index, and we can choose two elements in the range. Yeah, this is greedy. So it's let's say we have element a1, a2, a3, a4, a5, a6, a7. Now we have some special index. Let's say this is our special index. In one operation, we can choose some element L, which is on the left hand side of this, some element R, which is on right hand side of this, and we can flip all of these elements. So this is our problem statement, and the only condition is like L should be less than equal to a special index, and index should be less than equal to 1. So this is the only condition we have for us. And let's try to solve this problem. What we can do is, let's first independently count how many operations we need on the both the sides of special element to make everything equal to this element. Like, let's say we have element x here. Like, our constraint is like we must choose some element from here and some element from here, right? So let's try to make, or let's first just focus on this array. A0, A1, A2, and X. And what we can do is, like, we can greedily try to make everything on this side equal to X. And let's just assume that the right endpoint is this element only. So for example, if our array is 0, 1, 0, 1, then what we can try to do is, this is our special element X. Let's start from this element. Because this 0 is not equal to 1, let's flip all the elements in this range. 1, 0, 1, 0. Now this element is also not equal to 1. So let's flip all the elements again in this range. 1, 1, 0, 1. Now again this 0 is not equal to 1. So let's flip all the elements in this range. The elements will become 1, 1, 1, 0. And because this 0 is not equal to the original element, let's also flip it here. 1, 1, 1, 1. We need total 4 operations for left side. Similarly, we can do it for right side as well. Let's say we have X 0, 0, 1, 1, 0. And let's say this is also 1. Now this 0 is not equal to our original element. So let's apply an operation on this range. The elements will become 1, 0, 0, 1, 1, 0. Now this 0 is also not equal to 1 because we want to make everything equal to 1. Let's apply an operation on this range. 1, 0, 0, 1, 1, 1. Now if this is equal to 1, we are good. This is equal to 0, so apply an operation on this range. This will again become 1, 0, 1, 1, 1, 1, 1. And this is 0, so apply an operation again here. 1, 1, 1, 1, 1, 1. Total 4 operations again. And the idea is like you just look at the maximum of left hand side, right hand side, and print it. That will give you the required number of operations. The idea is like, let's say we need, this is our special index. We need 3 operations here and 7 operations here. What we can do is, for the first 3 operations, let's say we need operations 1, operation 1 here, and 7 operations on this side. These are the indexes where we need an operation. What we can do is, we can first apply an operation taking these 2 indexes. Then we can apply an operation taking these 2 indexes. Then we can apply an operation taking these 2 indexes. And afterwards, we can just apply operation by taking this element and this index. this element and this index, this element and this index, this element and this index, and we would be done. So like this would be the overall greedy idea over here. Any questions, anyone so far? Like here we have only one index that makes things a bit simpler. Okay, numbers are up to 2e5, so we will have to smartly do the operations here. Because k is always 1. Like x is what we need. We maintain an additional flag if we have flipped operations or not. If we have made odd number of flips, we should first switch the current value of j. If aj is not equal to like what we need, then we need to increase the number of operations by 1. And if all the bits were already flipped, you flip it, otherwise you don't flip. Similarly, we go for right hand side as well. And now we have to just print, we have to only print maximum of both the operations. Wait, what? Not really sure what's happening here. We have all the numbers. Okay. Okay. 1 second. Why am I printing odd indexes? Mhm. Mhm. This should be our solution for B. Let's also submit it. Any questions, anyone on the first two problems? Okay, I will wait for a couple of more minutes and then move on to the next problem. Let me see if there are some good enough solutions for the C that I can potentially explore. Okay, how to handle performance anxiety during contest. So one hack that I use is I do not look at standing and I do not look at number of solved problems. And that's how I have handled anxiety whenever I. Because if you see large number of people getting an AC on the same problem and you are not able to think about it, you will not be able to, by just looking at the increase in AC, neither would you be able to think about this problem, nor you would be able to think about any other problem. Same goes for the contest fee. So like the proven way for me to handle anxiety or in the contest is to just open this page in one go and never refresh it. And you can open all problems by clicking on complete problem set here. And this leads you to the AC problem. And do not open standing. And like that's where we are. Like, will you try C again since you didn't solve it in the contest? It would be educational to see your thinking process live. Actually, I have seen the solution of what's the solution for C. So at least I know what three conditions are there in this problem. So I will just take a quick look at if anyone has better explanation for C. Otherwise, we can try this. Um, okay, this was the condition that I could not guess. That's what I would say. Actually, I did not agree with this. Like among all the problems, F was the one that was a bit natural. Otherwise, everything was fine from solution. Okay, this is fine. This is also fine. The number of unit cells that you visit before moving to the start would be this, and it should be greater than n equal to n. Hmm. Where is that command? Okay. Actually, this command makes sense. So yeah, like overall, the idea is as follows for the problem. Yeah, I will upload it on my YouTube channel. Like, you can find it here. Like once. Hmm. Prakul has been working hard setting problems for Kotka. When he's deep into the thought, he likes jumping around his room in weird but specific ways. After some time, he wonders if jumping in this manner can cover all the tiles of his room. Parakul room can be considered as a grid consist of n rows and m columns. He started walking from A1, comma 1. If he is currently at I, comma j, then he can do either of the following: jump B to the right or jump A to the down, and each row is considered kind of like a cycle. A special restriction is that he can start with either move but must alternate between them. Let's first try to solve without this condition. Note that in his room it's quite special as it wraps around itself. Moving one step right from the nth column places him in the first column. Similarly, moving one step down from the nth column places him in the first row. Since he still has to work on problem setting, he needs your help. Determine if he can visit all the tiles in a infinite number of jumps. So the problem statement is as follows. So actually, I did solve problem A earlier, and you can probably find it on the VOD once it's available on YouTube or Twitch. So like the problem statement is as follows. This is the grid we have. Now I have a fixed defined size. Let's say for going right, you take jump of 3, and going down you take jump of 2. So let's say if you start from here, in the first turn you can choose whether you want to go right or whether you want to go down. Let's say we go down. Now once this is done, all your process is now fixed. After jumping down, all you can do is jump to the right 3 times. So you will come up here. Then you can jump down. You have to jump down. You will come here. Then you have to jump down 3 times. You can see like there are only 2 cells. So 1, 2. It says a jump after this will lead you here. So here, and you will come land here. Now you have to make jump down 2 times. Nothing is here. So first jump you will reach here. Second jump you will reach here. So once you try to stop jumping here, after one jump you will reach here. After second jump you will reach here. Then you can go to, you have to go right again. 3 jumps here. Again 2 jumps here. Again 3 jumps here. You will reach here. And then 2 jumps right back. You came again here. And you can see once you reach the starting cell, you will repeat the same process again. And you were not able to visit all of the cells here. So the problem asked gives us like this is the given length n. This is the given length m. The jump on right hand side is a. The jump below is b. And can you reach all the cells if you do this jump? If we keep jumping, So this is our problem statement. Any questions, anyone on the problem statement? Okay. Any questions, anyone? Okay, so the modular is another way to say like how do you make jumps here? Like for example, when you are on this cell, which is 1 0 1 2 0 1, let's do 0 based indexing. So this cell is 0 comma 0 0 comma 0 0 1 2 3 4, n is 6. This cell is 0, comma 5. 1, 2, 3, 4, 5. M is 5. This cell is 4, comma 0, and this cell is 4, comma 5. Let's assume zero based indexing. So, like what problem statement says is, like, for example, if you are here 4, comma 3, then when you do a right jump of 3, then you will reach 4 mod 6, comma 4 3 plus the jump size 6, comma 6, which is again 0, comma 4, comma 0. So like mod allows us to like figure out a cell on which you will land, but it's kind of like saying whenever you reach a boundary here, you land on this cell. Whenever you reach a boundary here, you land on the cell at the top. So the idea is like it's kind of cycle. Right side is horizontal is also a cycle, and the top is also a cycle. And that's what someone is trying to formally put in mathematical terms, this same thing. So let's first forget about the condition that you have to always take alternative type of moves and everything. Let's first say, like, if we had on a number line, or let's say we have a kind of a circle, and then this is 6 again. Let's put it as a circle, and once you jump outside 5, you reach back again. And let's say our jump size is 3. So you start at 0, comma 0. You go to 3 here. Then when you take a jump of 3, 1, 2, and 3, you will reach back here. Let's say our jump size is 5. So like when you have a jump size 3, we cannot visit all the cells. Let's say our jump size is 5 now. We start at 0, comma 0. We take a jump of 5. We reach here. Now when we take a jump of 5, 1. After one jump, we will reach here. 2, 3, 4, 5. We will reach here. The next jump will leave us here. Now let's take a jump of 5 again. 1, 2 will bring us here. 3, 4, 5. We will end up here. Now from here, if we have to take a jump of 5, 1, 2. After the third jump, we will reach here. 4, 5. We will reach here. After from here, if we have to take jump of 5, 1, 2, 3. After 4, we will reach here, and 5 here. And after that, if we have to take a jump of 5, 1, 2, 3, 4, and we will jump back here. So like if we have a jump of 5, you can see we have visited all the cells. If we have a jump of 3, we have not visited any cell. And like overall, the observation was, if we have GCD of len and jump size equal to 1, then only we will be able to visit all the cells. Otherwise, we will not be able to visit all the cells. How do we prove it? Let's say what would be the total distance we have traveled after k jumps. K into ln, right? This would be the total distance. K into jump. Sorry. And what would be the cell? And if we have to reach at, if we start from 0, and let's say after we start at 0, after k jumps, we reach at 0 again. Then what is the minimum such value of k? Find minimum possible value of k. Let's solve for this problem first, and then you will see like how everything falls apart. We started from 0. We made k jumps of length j, and at some point we will again reach back to 0. The question is, what are the minimum number of jumps we need so that we can reach k again? So the way it would be like, if we make k jumps and each jump is of length k, then k into j mod length should be 0. Because you started from 0, this is how you reach 0. Or we can say that k into j should be some multiple of length. Or k would be equal to I into L by j, where we have to now figure, like I would be some integer over here. Yes, you can rewatch the stream on Twitch as well, or you can also watch it on YouTube as well. Now what we know is, like, the minimum number k would be some multiple of L divided by j. And my claim is, like, the smallest number we can find over here would be like LCM of L comma j. Like k would be equal to LCM of L comma j. Like that's the smallest number which can satisfy only, that's the smallest number for which we can find some I. Or another way to look at it is like this. Let's say G is the GCD of L comma j. Then L becomes G and let's say smaller. And jump becomes G and small j. Like here I'm trying to prove it mathematically. Let's say if GCD of length and jump is G, then L would be like some G and some small l. Like you factorize L into two parts and you factorize J into two parts. Now you can write K equal to like this. And you can cross out this G, I into L divided by J. Now, like, because this was GCD, the LCM of these two would be 1 only. And like, what's the smallest value of I? So that like the smallest value of I we can choose over here would be like J only, which can make it a prime. And like we can potentially choose I equal to J, and this can give us K equal to 1. So value of K becomes L divided by GCD of like if we take this equation, the value of small l is L divided by J. It's equal to L divided by GCD of L comma J. Like this is the minimum number of jumps we need, and total distance traveled is zero is k, which was equal to L divided by GCD of L comma J. And total distance traveled to reach minimum is, or essentially like this is also the number of cells visited. Before we reach zero again. Like the number of cells, the number of jumps you make before you reach zero is also would be also be the number of cells you make zero. And if you want number of cells equal to L, and if you want this value to be equal to L, then the only way we can do is like this GCD is equal to 1. This gives us a condition that GCD of length comma J should be equal to 1. Then only we can visit all the cells before reaching 0 again. Any questions, anyone, so far on this condition? Like any questions, anyone? Like why GCD of jump and total length should be equal to 1? Then only we can visit all the cells. Like I can reiterate, like briefly explain the idea again if anyone wants to see it again. So overall, what we have tried to derive is, let's say after k jump we reach the starting cell again. So like k into j would be the total distance we have traveled. That should be some multiple of the total length because the mod we are taking. We tried to put equations around. We came up with k should be equal to I into L by j. And now we need to find some value of I where what is the minimum integral value of k we can get. So we tried to put g equal to GCD of L comma j and replace this L by GCD multiplied by some value and GCD multiplied by some value. GCD crossed out. So k became I into L by j. Now for minimum value of I, we can choose I simply equal to j only. This gives us like after L number of jumps, we can reach the starting cell again. And the value of L is L divided by G, which is L divided by GC. GCD of L comma j. So after these many jumps, we will reach the starting cell. And if we want that we have visited every cell before we reaching the starting cell, then this value should be equal to L. And the only way this value can be equal to L is this GCD is equal to 1. So this gives us two essential conditions for both the direction. GCD of A comma N should be 1 and GCD of B comma M should be 1. Otherwise, there is no way we can visit all the rows and all the cells. So this is the first version of the problem. And now the next part is again, let's try to solve the same problem in 2-dimensional as well. Same way how we did it so far. Let's say after t distance, after t jumps, we reach the starting cell in both the dimensions. So we will have t into A mod n equal to 0, t into B mod m equal to 0. And you can try to play around again here. And you will find like t is again equal to. So from the first equation, like t should be multiple of n, because we have already seen that GCD of n comma a is 0. So only after n turns you will reach m. T should also be the multiple of, like I am saying, t jumps horizontally, t jumps vertically. So overall 2t jumps. And like the smallest number that is multiple of both n and m is LCM of n comma n. Like this is the smallest time when you would be at 0 comma 0. And like this number of jumps in horizontal, this number of jumps in vertical. So 2 times LCM of n comma m after these many jumps, because half of the jump would be in horizontal direction, half of the jump would be in vertical direction. If you start from 0 comma 0, you will reach 0 comma 0 again. And this would also be the number of unique cells you would visit on the way. So this should also be equal to n into m. Because if you want to visit at least all the cells, then the total number of jumps you need before you reach 0 comma 0 again should be greater than equal to n comma. Now you can write the formula of LCM. Like we can use famous equation of LCM of a comma b is equal to a into b divided by GCD of a comma b. And if we replace it here, we will get 2 into n into m divided by GCD of n comma m should be greater than equal to n into m. You can cross these two numbers out and you form around, you will get GCD of n comma m should be less than equal to. So this is the third condition we have. Any questions, anyone, on these three conditions? And the code becomes like this. If GCD of n comma a is not equal to 1, you directly print no. If GCD of m comma b is also not equal to 1, you print no. If GCD of n comma m is less than equal to 2, you print yes. Otherwise, you print no. Any questions, anyone? A bit tricky problem to solve, but this was problem C. Any questions, anyone, on problem C before you jump on to problem D? Yeah, like actually, I don't know the recent problems, but you can definitely look at the rating in Celius.ua. Yeah, like man, if KFG is quite right. Like if you can play around with maths, then you will find this problem easy. If you don't, then you will find this problem hard. If I have to look at the rating on clist.by, okay, it's still calculating it, but it shows quite less because a lot of people got an ACA on this one. So let's move on to problem D then. Like this is same as the problem A, B, but now we have more than one special cell. So we have to think a bit differently here. Like how do you think of problem? Like see, how did you like? I tried to smash my head around solving with some GCD etc. idea. I tried to stress it, but eventually I could not solve it in the. And right now, the way I explain this problem is I looked at how other people have solved it. So like this guy explained it pretty well, and I simply explained this idea. So like the way we solve it is like you try to play around with mathematical formula. Yeah, like in short, you practice a lot. That makes sense. So let's move on to problem D. Flip the bit hard version. The problem is same as problem B, just that we have multiple special sets. And we can no longer use the original idea. Like for the sake of simplicity, you are given a binary array A of length n and k special indexes p1, p2, pk. It is given that initially values ai of all the element at special indexes are same. In one operation, you can choose a range such that the range contains at least one special index and flip all the bits for L, R. Flipping a bit changes 0 to 1 and 1 to 0. Let x denote the value at special index before any operations are applied. Find minimum number of operations required to make all the elements of the array equal to x. Okay, yeah, like I did assume that 2t operations are there. 2t minus 1 will possibly not be there or not sure. Okay, yeah, 2t minus 1 may be there, but yeah. Yeah, like the video would also be available on my YouTube channel right now. I don't know, like possibly Twitch does not allow it. So like after it's there, you can find the video here. Yeah, like actually you might be right that it could also be 2t minus 1. I did not try to solve it, and that's where we are. So like let's solve this problem a bit differently now. Let's look at the original array again. And let's say these are the two special cells. Let's also put some values here. 0, 0, 1, 0, 1, 0. Like all the special values are same. Like if we want to make all the elements equal, then can we also say that all nearby elements should also be equal? Like if all the nearby neighboring elements in an array are equal, then all the elements in the array will also be equal, right? So with this idea, let's see like what we need bare minimum. Here both the elements are equal. We skip it for now. Here one of the element is 0, one of the element is 1. So we must do something over here. Either apply an operation like this to flip this range, or apply an operation like this to flip this range. We need one operation where A1 is involved but A2 is not involved, or other way around, A2 is involved, A1 is not involved. Like we should have one boundary of one of the flip operation on this side. It can either be this, it can either be this like this, or it can either be like this. Then only we can have elements both a1 and a0 equal. Similarly, now 1 and 0 are not also equal. So we need one operation with the boundary here as well, either like this or like this. Let's try to figure out all such places. These 0 and 1 are also not equal, so we need one operation where we have some boundary here. We need one operation where we have some boundary here because 1 and 0 are not equal. We don't need any operation here because both of them are 0. We also need one operation where the boundary is here. These are equal, so we don't need anything. These are not equal, so we need one boundary here. So white spaces are the places where you need some boundary. If you create a box on which cells you are flipping, then at least one should be here. And now if I have to try to form this array like this, what I can possibly do, I can make one rectangle like this for the flipping. One rectangle like this for the flip. And one rectangle like this for the flip. And you can see with these operations, all the elements would be equal. Like, can you see why that would be the case? So this would be the main idea over here. We first try to figure out at what all places we need each operations by looking at the nearby elements. And if we look at spatial index as a boundary here, then what I can say over here is like let's say this is one spatial index, this is the other spatial index. Then you need two operations with boundary here, 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 and two operations with boundary here. This looks fine, right? Yeah, swap equal to rectangle, and that's erasing the border. So any question so far? Because like the next part would be a bit non-trivial, but I want to make like these analogies clear, like how I am choosing the boundaries of a rectangle first, and then how if I choose two sides, I simply call that as a rectangle and say everything between them flips. Any questions so far? Now what we need is we need to somehow form pairs here. We need to form pairs here so that we choose boundary on two different sides of a rectangle. Of spatial index. Or another way to look at it is like if you look at each of these elements as an array, where the array is like the number of boundaries, in this case, let's say 2, 2, 2. Then the way to look at it is like every time I have to choose two, Like my new array is like the number of boundaries I need between each part here, which in this case is 2 to 2. What I can do is like I can choose two indexes from here and subtract that value by -1. Now what I need is like the number of operations. At each time, we have to choose two different index. Index and subtract -1. Actually, you strictly don't need -1. You can also do +1 if you want, and the next time you do -1 as well. That also works. The idea is, let's say, for example, you have 0, 0, 0, 4, 0, 0. Then how will you do it? You will choose, let's say, let me put it this way. Again, the same boxes. And you need 4 operations here. How you can get it achieved? You can choose any point on the right hand side of any value. You can make first rectangle like this. You can make a second rectangle like this. You can make a third rectangle like this. And you can make a fourth rectangle like this. So this would be changed 4 times and you would be back at the same problem. So now this is actually a quite a famous trick. Like how do you pair elements in the pair of 2 and you use minimum number of operations? So yeah, it's for 0, 0, 4, 0, like you will need 4 operations, not 2. There is actually a video by CF Step over here, which you should definitely look at it. On like how do you find minimum operations here? Like you should definitely check out this. Like this proves like you have boxes like this, you have to choose two elements and how do you do it? Overall idea is as follows. Like we have two upper bounds here. Like because let's say A1, A2, A3, A4, A5. Then let's say the number of operations required would at least be maximum of all of these values, right? Because for every box you cannot remove two values from the same element. So like let's say if the highest value is 40040, then you need at least 4 operations to get everything right, because in this operation every operation for a particular element you can only decrease the value by 1. And also like what is the upper bound over here? I can also just say that like whatever the total number of elements, that sum by 2 would also be the minimum number of operations I need. Like if I need 3 operations in one partition, 2 in one, 5 in one, then 3 plus 2 plus 5, which is 10, 10 divided by 2, at least I need 5 operations over here. So overall what I am saying is like these are the absolute minimum values for the number of operations I have. That would be if I look at maximum element in this array, because every time I can subtract -1 from one index only, I have choose 2 index and subtract -1. So if the maximum is 10, yeah, it would be seal. Yeah, definitely it's a seal. Or like if you even treat it as float, because the number of operations is integer, it would become a seal. Like the smallest integer more than 2.5 is 3 only. So what I'm saying is, like, if you look at all the elements individually, the minimum number of operations would at least be equal to the what is the maximum element in the array. The minimum number of operations, that would is one way to look at it. And what I'm also saying, like, because I can subtract only two values at one point in time, so, like, oh no, at least it's not less than, I'm saying it's greater than. Yeah, like, two times sum you can also say it, but what I'm saying is, like, if I have 11 borders, because for every time I choose two values, I need at least six values over there. And the strong claim over here is, like, these are the, if you look at these two values and print the integer, the smallest integer that satisfies both of this, then you are done. So, and I think this is also the idea on, like, the same idea like CF step has, like, he explained these two borders and try to explain a proof on how these two borders are achievable. What I'm claiming is, like, the answer is simply this over here. Like, there is potentially off by one value somewhere because of even odd, but overall this is the idea for this problem. Any questions, anyone? Like, you can view the stream later on my YouTube channel, or, like, it would also be available here as well. So, like essentially, like, this is the solution. Like, you need to first figure out what all places you need at least borders for a rectangle, and then you look at which component has the maximum number of border, that is the lower bound on your answer, and total number of borders divided by 2, that is also the lower bound of your answer. So you just take maximum of these two values and print it. And yes, maximum of max A and some A by 2. Like, you potentially need some off by one value over there as well, but yeah, essentially that's the idea. Like, it's plus minus one over there. So I have marked all the special indexes first. So if this is not the first index and current value is not equal to AJ, then we need a border between these two indexes. Now, if current cell is special one, then you found all the borders you have found so far and you reset your counter again. And at last also, like, you put whatever borders you have got over here. Now you look at maximum of sum also. maximum. Sum divided by 2, we have to take C here. So this is, I am claiming to be the answer. I expect at max it can be off by 1, and then I will try to figure out the conditions where we need off by 1. Mhm. Mhm. And okay, this should again be. So here it expects the answer to be 2, but I'm getting zero. DVD. So like the idea is like inside every border you also need even number of operations there. Like so this gives us the required maximum and this should work. Now wait 1 second. Let me just. So I think in contrast, what I simply did was this was the first idea WA on this was okay. Total number of operations by 2. That this makes sense. And maximum is plus 1 only. Okay, I need a maximum here. Or I can just avoid this maximum here. Wait, what? 1 second. Okay, even for some you need to take it over there. So not just some. If like yeah, like you need you can just keep this one. So yeah, like what I did was like how did that plus one came? Yeah, I am done with the grid covering. One more observation here was like inside on every side you need even number of operations. You cannot have odd operations there. Like like here you will need four operations. The primary reason is like notice the fact that how we are coloring here is based that nearby elements are equal. What the problem I have solved for is how to make all the elements equal. That's how we divided that yellow border, right? What we really need is all the elements should be equal to the initial value of special elements. So value. And if you need this, like for example, if you have only three indexes here, then doesn't really matter how you put elements here. Let's say you made this rectangle, you made this rectangle, you made this rectangle. In this case, due to this operation, this will remain same, but now this will be flipped. Like you need two times operation from here as well. One more operation here so that this value again becomes the same. So that due to these conditions, like all the elements should be even in my border. And to make it even, that's why for all the elements odd, I have increased it by one. Then look at the max, look at the sum by two, and that's your answer. Any questions, anyone? E and F would be the last two problems, and then we will wrap it up for today. Yeah, now I believe like it is an interesting problem. Yeah, like video would be available on YouTube as well. You can go back there. Like once I'm done, I will upload the video there, and you can go back there. Or here also, I will upload the highlights, and you can go back there. Like today's contest was interesting. Now, like now we'll go back and appreciate the beauty of mathematics here. The contest is definitely interesting. But in the contest, it was me trying to somehow get an AC with some proof by AC, and you definitely don't enjoy that moment. Yeah, definitely math model. I liked F more than all any of the other problems. And like I started 15 minutes late, and And my problem statement is I started after 15 minutes late. So within 2 minutes A, then next 16 minutes B, then trying to jump around here, and after 30 minutes I got D. Then after 50 minutes it was F, then back to E and no C. Let's move to problem E then. You are given a permutation P of integers 1 to n. For an arbitrary permutation Q of length n, we say that index J dominates index I if and only following conditions are true. J greater than I, Pj greater than Pi, Qj greater than Q. You are also given an array D of length I, where Di denotes number of indexes that dominate I. Your task is to construct a permutation Q of 1 to n such that every index I, the number of indexes that dominate I is exactly Di. If such Q queries exist, output any value 1, otherwise output that it does not exist. So we have to figure out some permutations based on some conditions and all. Let's try to solve a simpler problem first. Let's forget about this problem. Let's solve a simpler problem. You are given some value A0, A1, A2, A3 up to AN minus 1. Now you have to construct a permutation P0, P1, P2 up to Pn minus 1 such that if we count the number of indexes, J, which is between 0, comma I minus 1 and Aj greater than A, then count of or Pj greater than Pi, Pj greater than Pi, then count of such index is equal to Ai. So essentially what we are saying is we have to find a permutation. We are given an array A. We have to find a permutation P such that for every index, if you look at the number of elements that are before it. Okay, sorry. Or let me take a live example here. Give me a permutation of length 6. Give me a permutation of length 6. 1, 3, 2, 4, 6, 5. How many elements are more than 1 before this index? The count is 0. How many elements are more than 3 before this index? Count is 0. How many elements are more than 2 before 2, which is 1? How many elements are more than 4 before this index? This does not look like an interesting permutation. Let's make it this. Let's use this permutation. How many elements are more than 6 before this 6? The count is 0. How many elements are more than 5 before this? The count is 1. How many elements are more than 4 before this? Only 6 and 5. The count is 2. Now let's say we are given this array and we have to find a permutation like this. Like number of elements which are more than 6, like 1, 3 and 2 are not less than 6, not more than 6. For this element, there is only one element more than this over here. There is only one element more than 2 over here. Now, if we are given an array A like this, how do we find such a P? One hint, like if there is a valid array, then the permutation is always unique. How do we do this? Let's look at this 0, 0, 1, 0, 1, 2. This is what we have. Let's start by creating this permutation. Let's say we focus only on this element. And like if we have to just create an array which is answer for this, then we have only one, right? Let's say we have array which is equal to just 0. Then the only way to create a permutation is just length 1 is just 1. Now let's say using this, we create an answer for array equal to 0, 0. And now we have to fill in something here. Now because the number, no element before it is more than 0, so this should be the smallest number here. How we can do it? What we can do is we can keep this as 1 and keep this 1 to 2. So our answer becomes 2, 1 if our array is 0, 0. Now let's try to find, using this, let's try to find answer for 0, 0, 1. Now we have to fill in some number here such that there is at least one element more than 1 over here. So between 1 and 2, like I can technically choose 1.5 here. Or what I can do is I can choose the element which is if among 1, 2 and 3, because I have to keep one largest element, so I can keep the second smallest element from this array. So what I am saying is I will fill 2 here, and all the elements which are greater than equal to 2, I will increase them by 1. So my permutation becomes 3, 1 and 2 if my array is 0, 0, 1. Now you can keep going on like this. The next A needed was 0, 0, 1, 0. If I have to add 3, 1, 2, some element here such that the answer is A 0, 0, 1, 0. Then what is the smallest element among 1, 2, 3 and 4? The smallest element is 1. So I should somehow fill 1 here, and all the elements that are more than 1, I should increase them by 1. This would be my answer if my array was. Now, did you got an hang on of the idea of what I am trying to do? I am solving it for each starting subarray, and when I have to append a new element, I see which element I should put over there so that my condition for this index satisfied, and I increase all the elements that were more than that by 1 to somehow keep the relationship. Now you needed 1 and 2. Now I need to put some element here such that 1, 2, 3, 4, 5. There is at least one element over here. So in that case, I should put 4 here. So I can put 4 here and increase this 4 by 1. So this would be my answer for 5, 2, 3, 1, 4. This would be my answer for 0, 0, 1, 0, 1. And now I have to put somehow 2 here as well, and I need 2 here. So I have to choose the third largest element from 1 to 6. Third largest element from 1, 2, 3, 4, 5, 6 is 4. Or okay, 2 I need, so I need third largest element. So I put 4 here, change this 4 to 5, change this 5 to 6. So my answer becomes 6, 2, 3, 1, 5, 4. Or I think I matched up somewhere. This does not look like the permutation we started with. It looks like I matched up over here. Okay, looks like I did calculated something wrong over here, but did you got overall idea? This permutation is definitely not right. But the overall idea is like we keep adding one more element at the end. Whenever we want to add one more element, we see what element we put over there and increment the remaining values to get our desired result. And like we will use the same idea over here. Like if we had two permutations, we can see what all indexes can increase the value over there and try to choose it similarly. Like even the permutation 2 does not changes a lot. It's just that like we can skip all the indexes where this condition does not hold. So we have a list of indexes that can dominate my current index. And among that, I try to choose the index such that the maximum condition still satisfies. So I start from the last index. I am using zero-based indexing. I first try to figure out all the q that are larger than this. If pj is greater than pr, then this element can potentially dominate it. Put qj over here. Now these are my indexes. And total I want large index is equal to dr. And if number of larger index is less than key, then I cannot find anything. I simply break it. Otherwise, I try to count all the elements. Like I try to keep increasing my current value. I remove the largest t elements from here. First, I say that this should be the value I should keep and increment everything more than current as my value. So the idea is like choose the t largest value among all of these values. Okay, QJ. And overall, this was the answer we had. Default should be easy. Let me give it a shot. Like there should be some off by one or two, but overall, this was the idea over here. And I frankly did not bother showing. Yeah, this works. Any questions? Anyone on problem E? So it's again a greedy problem. Yeah, looks like back is not available on Twitch. So once the video is over, the VOD would be available on YouTube. So you can go there and see. F would be the last problem we would discuss today. Any questions? Anyone so far? Yeah, I will try to explain problem statement as well. Okay, the problem seem easy after your explanation now. Thank you. In that case, don't forget to subscribe on like or follow on Twitch and YouTube because I'm planning to do more post contest discussion streams like this. Interval game. Alice and Bobs are playing a game involving two intervals L1 and R1, L2 and R2, constrained by indexes x1 and x2 respectively. The interval satisfied L1 less than R1 less than x1, L2 less than R2 less than x2. The game is played as follows. In one turn, a player must choose one of the two intervals and perform exactly one of the operations: decrease L or increase R. The player who cannot make a valid move loses the game. The game setup proceeds in two steps. First, Alice chooses L1 and R1. That must be a valid interval. Then the second interval is chosen randomly. Now, Alice has to choose interval in such a way that the probability of him winning is maximum possible. A lot of stuff here. So let's say first we are given, let's just look at, we are given a number line. One number line is up to x1. One number line is up to x2. And in both of the number lines, we have some range of chosen number. When players are playing a game, they can either shift this border to right, or they can shift this border to left, this border to right, or this border to left, and this border to right. These are the four things you can do. At the end of the game, what will happen is both the borders would be like essentially it's like you have some range of element, you stretch one of the borders to the end how much you want. Eventually what will happen is like this border will be fully occupied, this border would be fully occupied. Now at this point the game is over, and whose turn it is, the player whose turn it is can no longer stretch this, and they will lose the game. Any questions so far on this game setup? Now what problem is saying is, Alice is a smart guy. He will choose this first border based on some random things he wants. So Alice will look at something and figure out like what border he wants to choose for the first element. And second border will be randomly chosen among all of these possible borders. Like in this range, there can be many right borders. Like this can be one border over here. This can be one way over here. This can be one over here. And it's equal probability that any one of possible segment over here would be chosen. Now what Alice has to do is he has to smartly choose this first border such that the probability of him winning in a particular randomly, where this is chosen randomly, it becomes maximum possible. Any questions so far here? Like you have to smartly choose this border, and this would be chosen randomly so that probability of you winning the game is maximum possible. Let's first forget about this one. Like let's say you have already chosen two borders, forget about random and all. How do you figure out who is going to win? So for example, this is a number line from 1 to 10. This is a number line from 1 to 7. Here you have 3 to 5 already chosen. Here you have 2 to 6 already chosen. Now if this is the state of the game and Alice is going to play, can you figure out if Alice can win with these borders or not? So now let's look at it differently. What are the possible number of moves over here? You can either stretch by 1 or 2. Like you can increase this border by length 2 only. Here you can increase this border by 5. Here you can increase this border by 1. And here you can increase this border by 1. So if I write these numbers down, 2, 5, 1, 1. The problem is as good as you have an array of 4 elements. You can choose any of the numbers, or like let's say you have 4 baskets with coins in it. In your turn, you can choose one basket and remove some of the coins from it. And the person who cannot remove any of the coins will lose the game. So like essentially saying you have an array of 4 elements. Yes, decrement them by arbitrary number, but you cannot go negative. And once all the elements become 0, the player who is supposed to play will lose the game. So I won't go into the proof and all, but like this is what the NIM game is. This is the most basic NIM game. Like the NIM game is look like you have a piles. Each pile has some numbers on it. In your turn, you remove arbitrary number of piles, and the one who cannot win loses. What I will use observation from the NIM game is like the starting player can lose if and only if A1, XOR, A2, XOR, A3, XOR, A4 is 0. If this is the condition, you will lose the game. If this XOR of 4 the elements is non-zero, you will win the game. I won't go into the proof of this. You can read about nim games, and like this is the most classic formula over here. Like you can look at this lead code or anything. So like sparse joint theorem and all is there, but yeah, like this is one idea over it. Now with this observation, any ideas on how do we solve this problem? So now you can look at your original interval, both the intervals independently. X1, 1, L1, R1, 1 to X2, L2 to R2. Yeah, I think that's fine. No need to subscribe here. Like you can just follow and that's all. Like subscribe is for YouTube, follow is for Twitch. Yeah, I think like no need to spend money over here. And that's it. So yeah, like just follow on Twitch and subscribe on YouTube, and that's where we are. So the idea is like if you look at this, your A1 is equal to L1 minus 1. A2 is equal to X1 minus R1. How much you can spend? A3 is equal to L2 minus 1. A4 is equal to X2 minus R2. Write these four conditions. Or I can put it like this. A1 plus A2 should be less than X1. Like for each value of A1, A2, you can try to figure out which value is it. And A3 plus A4 should be less than equal to X2. Right? We have to choose four elements, and this is the condition. Now this would be chosen randomly. And this you have to choose smartly. Yeah, like interval size is 0, then like two elements would be equal, and you can try to figure out. Like if both A1 and A2 is 0, then you choose both left and right hand point. Now, what's the most important thing over here? Do we really care about A1 or A2? All we care about is for some XOR X, A1 XOR A2. What are the number of ways to choose? Let's call it B1. And like we don't really care about A1 or A2. What we need is for a given XOR 5, what are the number of ways to choose element? Similarly, we can try to find it for every element, right? Like what we need is distribution of right. So let's say sum of 0, 1, Let's say somehow we know that there are 5 ways to choose XOR as 0. There are 3 ways to choose XOR as 3. Like let's say there are 0 ways to get XOR 2. There are 1 way to get XOR 3. There are 10 ways to get XOR 4, and there are 2 ways to get XOR 5. Let's say this is for interval 1. Similarly, if we know two, 5, 4, like let's say somehow we know like what would be the distribution of XOR in both of these intervals. Then using this data, can you figure out what would be the least value? Because only when the XOR is 0, you lose the game, right? So for example, if you smartly choose XOR to be 3, then as long as XOR is not 3 for the second interval, which is this and this would be your number of ways for you to win. So what we need is, for both of these intervals, the graph of how many XORs we can get for each of the intervals. And if we have this graph, once we have this graph, using this graph, we can figure out like what should be the XOR we should choose smartly on the interval 1, so that your probability to win on this graph is maximum possible. Simple way would be like you choose at least one non-zero element and such that this value is small as possible. So based on this, like if you choose XOR equal to 0, then you will lose the game only 2 times. Or if you choose XOR equal to 6, then also you will lose game 2 times among all the possible ways. If you choose XOR as 5, then you will lose game only once among all the possible ways. Any idea, like once you know this distribution graph, how you can figure out which XOR to choose from? Like overall, it would be choose the minimum value among the second graph. So like our problem reduces to figure out this distribution of XORs in the given interval. Once you have it, you are done. So what we need is A2 for I1, A3 XOR A4 for. Once you have it, like it will become simpler for you to figure out minimum value and everything else. So now our problem reduces to, for a given value I, find number of ways to choose x1 comma x2 such that you are given, let's say, some element, some value L. X1 so x2 is equal to L, and x1 plus x2 is less than equal to I1. How do we do this? Now you know that once we can figure out the number of ways to choose x1 and x2, like the remaining problem will become a bit simpler. The idea is like we can use a bit of famous equation. X1 plus x2 is equal to x1 XOR x2 plus 2 times x1 and x2. Like you can also derive it. Like if you have 0, like if this is the let's say this is the bitwise X. Then for each bit individually, value of XOR would be for 0, 0, 0, 1, 1, 0, 0, 1. Value of AND would be if both of them are 0, 0, 0, 1, 1, and 0. And some would be like this. Here it would be 0, 1, 1. Here you have 2 bits. Here also you have 2 bits. Here you have 1 bit. So you can see like y is XOR plus 2 times AND is equal to sum of 2 elements. So the idea is if we have a fixed XOR L, then A plus B is less than equal to is less than I1, right? If we replace XOR plus 2 times of AND is less than equal to I1. So we can say that AND should be less than equal to I1 minus L by 2. Like L was the XOR we needed. Now based on this, like we can try to put numbers on each of the bits and try to figure out number of ways to choose X1 also. For each bit, if XOR looks like this, then we can try to figure out AND. Let's say AND looks like this. 1. Then the way it would be like this is like A, B. Because the AND is 1, XOR is 0, number of ways to put bits here is 1. AND is 0, XOR is 1. Either it should be 1, 0 or 0, 1. Again 1, 0, 0, 1. Both of these are 0, so the number must be 0. 1, 0 again, like this should be 1, 0, or this should be 0, this should be 1. And both of these are 0, so this should be 0. So now you have to figure out how many different AND you can get and how many XORs you can get, and you flip by 0, 1. And I think if you have made it so far, I will probably skip a lot of details here and I will mostly jump onto the code. It's been around 2 hours as well. And if you can see this, then you would be able to figure out the rest of the ideas looking at the code. So I'm mostly skipping the rest of the explanation, and I believe code should be set. You would be able to derive the remaining details. First, given x1, x2, let's figure out the XOR graph for each of these. For each element, we try to figure out the number of ways over there. If our XOR is exa, then the AND would be x total maximum possible sum minus XOR by 2. This L I have decreased by 1. So now let's look at all the bits here. If a bit is present is 1 in the XOR, then either your A or B would be 1, 0 or 0, 1. So the number of ways would multiply by 2. or if the current bit is less than equal to the end, then either you can make both of the elements 0 or both of the elements as 1. So I somehow keep this bit with me for now. Now what I need is possible sums using these bits such that their total sum is less than equal to this and of the numbers. Like this is again knapsack. So this is the knapsack problem we have to solve for. This can give us the number of possible ways to choose them. Now you can probably try to do recursive bit mask, etc. I used binary search here, but you can also use some DP as well. My idea was like I can try to binary search on the possible sums, try to get the things here. But you can also write a DP for this as well, a recursive DP, and that would also work. So I'm not going into the details of the DP, but I think that this is one homework exercise for this problem. Like my idea was like I can binary search on the number of ways, and the increasing ways would be bits only. So if sum of all the elements is less than equal to the given end, then return you can choose all the sets. Otherwise, you can binary search. You can find the mth largest sum abusing the fact that all the numbers are powers of 2. You can use some bit mask etc. there and check that ith largest number is less than equal to the given max or not. You can go there. Now, once you know the graph of this, let's first choose the XOR for it. If there is no way to get this XOR, then we should skip it. We cannot choose it. Otherwise, if what we need is we can resize B to the given form. Now, if number of ways to get this XOR is less than what you have to essentially find the index for minimum element in B, where the XOR A is non-zero. Now, this would be your XOR because you choose the minimum element in B so that the probability to lose number of ways you lose is less possible. And then you try to find one range where you have the given XOR. You choose the left index. Right index becomes Susan XOR minus R. If this is in the required range, you print the two endpoints and you break it. Overall, this would be the solution. I have skipped few parts over here, but I think like these are fun exercises to solve. Any questions, anyone? I think it's close to 2 hours now, so I am planning to wrap it up. So yeah, like I am also planning to be a bit regular with lead code streams as well. So you can follow me on Telegram or somewhere where I will post updates about. Yes, I will upload this stream on YouTube. So yeah, like the stream would be available on the YouTube channel. Once I wrap it up, I will just go and upload that. So you can go back and read the explanations again if you want. Okay, last couple of minutes. Any questions, anyone related to any of the problems in this contest or anything in general? So if there are no questions, then thanks everyone for joining in today. And I haven't read G and H, so I don't know how to solve them. Thank you everyone.